So let me move to some examples here then on how to apply this. So you can actually compare the theory of elasticity to strength of materials by comparing the dimensional stress to the dimensional distance R over A. And it turns out if you use theory of elasticity with area stress function, you get this curve. So the stress varies across the thickness in this way. And I'm using a B over A equals 4. So what that means is that I'm using outer radius, say, of 8, but inner radius of 2, say. So that's 8 divided by 2, that's 4. So that's what you're seeing there. And then this is the dimensional distance R over A. Obviously, the inner radius should be 1 because R is A at that point. And then when I go outwards, then I get R equals B, which is B over A equals 4. So what I'd like you to do for 100 points extra credit towards your homework, um, if you were able to reproduce these two plots using Winkler's formula and the theory of elasticity for square cross-section. Square cross-section. So you should be able to do that because I gave you the formulas for Winkler's. I gave you the formula for Winkler's just for moment applied. Just moment applied, derive it. You have this formula, you know A, you should be you know what the A is for rectangle, square cross section. You will have to come up with a B over A of 4. So come up with that example for you, and then and then plot this in a non-dimensional way, the way I did it here. So you can see that Winkler's equation, which is simpler, matches the Airy's equation very nice. So you can see this is a very nice match. Here, what I do is the same thing, but with shear load applied here at the end. That shear load gives you also not perfect match, but it's not too far away. And for this one also, we'll give you, well, I won't give you anything for this one. But if you want to try, try. But you should be able to plot this as well using the Winkler's formula and also using the theory of elasticity, because I gave you the formulas for those. Let's move to an example. What is the stress distribution on this curved beam using Winkler's formula? So I give you this curved beam with a moment. I give you the inner radius A, the outer radius B. So the first step is to define what R over H is. So R is the distance from the center point to the centroidal axis. And that distance is R. So that's A plus B over 2. And H is the thickness, which is B minus A. So that's easy. That's I just wrote it in a very simple way so that we can use non-dimensional quantities later, because that makes life easier sometimes. And B over A is just simply, you can write this, you can solve for B over A very easily. You can solve for B over A if you wanted to. This just show you can manipulate the equation different ways. If you use a theory of elasticity, I already gave you the formula for this. Basically what I'm showing you is how to develop this curve. I'm telling you how to do it, so you can replicate it yourself at home. So the area stress function, you can write it very nicely. You can make it all non-dimensional, like you saw, B over A, B over A. Very nice, R over A, because you're gonna need the R over A here. You can see R over A at the bottom. And then B over A is 4. So to be able to plot that, you need to write it in a simple way. I gave you this formula already, by the way. I already gave you this earlier. We covered it for area stress function. Just plot that. And then you'll replicate that for Winkler's formula. The formula here, to those that are confused about sign convention, is the opposite, it's negative now, because the moment is applied differently from how I derived it for Winkler's formula. Earlier, I had the moment applied that way, but this way is applied the opposite. So you can use Winkler's formula again, but put the negative sign there. And when you do that, and you make all this with the correct variables for a square rectangle, you'll get this formula you can plot. But I want you to walk yourself through all these steps, going from here all the way to here, because all I did was to substitute. For example, R sub n is this, A sub m came from the table that I showed you earlier. All those formulas are given, and all you have to do is simplify to have it so it's all non-dimensional. Non-dimensional is very helpful, and I invite you to do that in the future, because you can actually solve a lot of problems quicker by doing that. And if you did this too, steps, you will see that everything plots very nicely. The more basic approach that you may have learned back in mechanics of material is that stress was my over I. This totally ignores the difference between the neutral axis and the centroidal axis. Have you seen this formula before? My over I, mc over I, maybe you saw that. Maybe you saw mz over I. Who cares about the variables, right? The important thing is this moment times the distance from the neutral axis divided by the moment of inertia. That's what this formula is. You could also use this formula. It will be off for curved beam. It won't be perfect because a curved beam has a accounts for the distance between the neutral axis and the centroidal axis. Well, this formula does not account for that. Oh, so I plotted all three. So 1, 2, 3, all those plotted. And what we're doing here is varying R over H on purpose, and comparing strength with Winkler's theory against elasticity and the basic strength against elasticity. And you can see that as R over H goes higher, which means it looks more like a straight beam, the strength of elasticity my over I matches closer to what Winkler is. In other words, if it's more curved compared to straight, then it's going to be off from each other. The Winkler's formula is very close to elasticity. It doesn't matter what ratios you choose, because the theory accounts for the distance between the neutral axis and centroidal axis. And you can see here everything plotted for you, so you can see that the basic strength of materials my over I does not match the strength of materials or area stress functions for that matter. But these two match very well from each other. Personally, I love this formula a lot more. This is way easier to memorize than this formula, area stress function. Again, this is an approximation. This is more close to reality. But it doesn't matter because both are giving very good answers, right? And it's cool that Winkler's figured that out. Here's an example problem of a cross section that looks like a hook that you see here. A load is applied on either direction. And in this case, what you see here is that we need to calculate the maximum compression stress and tensile stress. So I do a free body diagram. I cut it here. I'll cut it there. I must have an axial load that's 9,500 because it needs to balance that one. And I also have a moment. That moment is 9,500 times that distance all the way to this point. And that you should be able to figure it out. It's good to kind of plot what we're looking at. This is a square here that we're looking at. We're looking at that cross section. So draw the square. The radius is A, inner radius, outer radius is B, right? And so you should be able to do the calculations from there. Okay. So you can see here all the different parameters we have. Calculate the area, cross-sectional area, 50 by 50, because we told you that it's a square cross-section 50 by 50. So calculate that area first. Calculate A sub n, which comes from those tables I told you about. That gives you R sub n. And then calculate the centroidal axis, which is 80. So all the way from here to here. And then from here to here, the average gives you this point here. That's 80 plus 30 divided by 2. That's 55. And I think I made a mistake. 50, B here in this case is a width, 50, while C is the outer radius. My bad, correction. But 80 plus 30 is 110 divided by 2 is 55. Now I have all my parameters defined. I can now calculate the hoop stress just using this simple formula. The axial force is given to you 9,500. The area is given to you 2,500. And just plug in all these values, and then you get the stress in the inner fiber. For the outer fiber, for R, select 80 instead of 30, because 30 is the inner fiber, while the outer fiber is 80. So plug that in, and then do the calculation to get negative 49.3. I think it will make a lot of sense to you that it's negative because I'm taking this hook and I'm applying a load like that, which makes sense that this should be in compression, this should be in tension. And that's exactly what you see coming out of here. Another problem real quick, you can do this at home, so pause the video and kind of do it yourself. But here's a hook and I apply a load P. Where's the max stress? It's going to be here in cross section AB, because that's where you have the maximum moment. Very simple approach again, using 3 different formulas, the curve beam formula. So again, calculate all the different values. A, Ri, R naught, Rn came from that table. Remember, we talked about that, and the cross section is given to you. And then you can calculate the distance between central axis and neutral axis. So just calculate geometry first, all the information for that. And then notice here how this moment is this load P times this distance R, which is 50. So P times R is the moment that is acting here. And then you have that P also. So Winkler's formula can be applied very quickly. P over A plus, and then you have the formula for moment times R minus Ri divided by AERI. This all came from the formula we saw for Winkler's formula. I'm not asking to memorize, but just use it. And then when you go through this exercise, you get 97. For point B, the outer fiber, you get this value minus 50. That makes sense because I'm applying a load this way, which is causing the hook to be in compression this way while it's in tension in the inner surface. You can use a simple formula back on mechanics of materials, my over I. You know how to calculate the moment of inertia for a cross section. It's 1 over 12 BH cubed. The moment is 300 times 0.016. We know how to do the moment calculation because it's that load P times that distance R, and that's going to give you that number. And finally, you can do the calculation using Airy stress function, the same formula we gave you before. I gave you this formula. And what you notice is that the hoop inner fiber and outer fiber is within 5% using the Winkler solution. I think you can check it. It's going to be very close to the Winkler solution, but off from the basic mechanics of material. I do want to thank you for attending to this lecture.